Hello everyone. First thing I want to apologize because my voice isn't right. Uh, in, right now I'm feeling bad. I'm feeling something weird with my voice. But I will try to explain what I did. First, we will launch the application that I did. Everything is on my GitHub. I will post on the description of the video below uh, the repo of GitHub. So let's see what I did. We will launch the Jetbot differential drive package that I am working. ROS launch Jetbot Jetbot and Gazebo. Yes. So uh, first thing that we'll try to do everything is to launch RVs and to launch Gazebo with predefined work. In the end, you can control the robot using the RQT interface for robot steering. This one. So let's finish. Let's wait to finish when Gazebo is ready. Okay. When Gazebo is ready, you can control the robot. Just let's turn the robot to the left just to see. Here we implemented ROS controls. And also we have a view of the camera if we go to RVs. So when the camera is not displaying anything because I have a code can here and in a moment will appear. Here it is because the robot is right there. And also you can navigate. Right now you can navigate freely, but the topics are working. ROS control is integrated with the bot, and also we have the camera view. So let's explain what we did. Okay. If you don't know what is the Jetbot AI Kit, it's practically a differential drive robot, only two wheels, two casters front and back, a camera. This is a new version because my version has a fixed frame here. You cannot move the camera. It's always looking angled at looking down in an angle way. The Jetbot AI Kit is a kit for autonomous driving or deep learning if you want. It has wireless interfaces, Bluetooth and Wi-Fi, on all the interface available of the Jackson Nano. And this kit doesn't come with batteries. You have to acquire separately, but the kit is pretty awesome. The documentation is, I think, is good. You have all the documentation on the wiki page of Waveshare and so on. Also, Waveshare sells another kit for autonomous driving, but with Ackerman steering. This one, let's see. This one is with Ackerman steering here. So there are two kits that you can purchase, but let's concentrate in the application here. If you see the tree of my project, you have a configuration folder, the image folder, the launch files folder, the RVs folder, the URDF folder, some videos if you want to see all my results, and also in the image folder are results, the Word folder, the CMake leaks, the package, and the README files, and the README file, I mean. So let's see what is in the CMake list and in the package XML. So the CMake list only prepares the project to make with Catkin. We are using RVs and URDF basically. On the package XML, our dependencies are the joint state publisher, RV, Sacro, and ROS launch. Okay, first, what is URDF? URDF is a unified description format for for describing robots. It's a XML file format. Basically, if you see this one, let's preview it. Here is my Jetbot. That's the thing I told you. My frame is fixed. I cannot change it. It's always looking to the floor. So how is this thing working? How we can make a robot in URDF? So you have to go to the ROS wiki page. Look for URDF, but basically I will explain the URDF, the basic URDF, this one, because the other is more complex. It's using Sacro. This one, I have here all the colors for the Jackson AI kit. As you see, you got black, white, blue, green, soft blue, and so on. This is the chassis body. It's a box. This one. This is the link for the shaft. This shaft. This one here, and this one here, left and right. Because you here only can do boxes, spheres, and cylinders. For displaying it, I made one cylinder. The radius of this cylinder more wider than this other, and this wide cylinder is a little bit over displaced on this direction. Next, we have here also the right wheels, the caster wheels, in the same way that we make the URDF file. Basically, the URDF, you have to get a link and specify which one is the parent link and the child link, and name that a join. You have links and joins. Next, here, this is everything about the caster wheel. So the caster wheel has 3 cylinders, 1 big cylinders and 2 minimal cylinders here, and the caster ball. This is the caster ball. This is the same thing, but for the back caster ball. The left and right antennas. Here, it's practically a cylinder and a sphere on the top. It's the simple thing to do. And also you have the camera mount is long because it's pretty complicated. Not complicated, is a little bit to work with that, because you have 1, 2, 3, 4, 5, 6, 7, 8, 9 pieces. That's our 9 pieces. And this one I just only put a block representing the Jackson Nano and the motor driver. This one here, this is the interesting part. If you want to make an interface with Gazebo your model, you have to include ROS controls. ROS controls are in this way a plugin that you can use to interface Gazebo and your model using URDF. So this is the basic example of the URDF. If you want to control only, if you want to view, there's another thing that we must do. So this is the basic example, just only visuals for the model, but there are also other things that we can make with the URDF model, for example. And this thing is like 474 lines of XML, but you can use a macro language named Sacro. So Sacro is a language, macro language to define robots, also using URDF. Here, I simplified everything that you got on the first file, this one, and also I added another things that you can add to the URDF file. For example, you can add inertias that are necessary for the simulation part. You can also add the camera plugin for interfacing Gazebo. That part I made it using uh, here on Sacro. So first thing you will see here, I made include files for all my Sacro macros and some constants. Here I specify the chassis macro that practically examples, and those other ones are calls from macros that are on the include file. The other ones are fixed ones because with Sacro you are trying to do functions, but if you see what can we do with Sacro is a function for the shaft, the wheels, the antennas, the caster wheels. It's not uh, it's not pretty useful to do. Example, uh, a Sacro macro for this box or this box because they are fixed. We know the size. Probably we can automate it a little, but I think it's an effort that you cannot, you must not do because with Sacro we need to simplify things. So that's the goal of Sacro. So next, returning to our model, you see that it's pretty simple. The main, let's say the main file, and let's see what is included on this one, this file that is named includes Sacro. So includes, the only thing that have are all the files that I'm using. Practically are macros that I'm using. I have materials macro, I have the Gazebo plugins, have the transmissions macro, macro for inertias, macro for antenna, macro for the wheels, the other wheels, and these ones, this macro for the caster wheels. So you see the structure that I'm trying to do. If you are in a big project, you practically you will try to make the things very clear. So that's what I'm trying to do. Let's see what is inside the inertias macro. Inside the inertias macro, there are the calculations for all the inertias. We only need the upper diagonal, so these elements, these 6 elements, IXX, IYY, IZZ, and those things above, that's all the inertias that we need. So because URDF description format we can only do uh, boxes, spheres, and cylinders. That's why I have only those figures inertias here. Next, okay, here in Gazebo I have all the physics situations. That's what I made it here. Here are, this is an interesting part. I have the ROS control, the Gazebo plugin for ROS control, and the camera plugin. One thing to note that could give you a headache. You need to put the camera the frame name here, not here. For better understanding, you must do it, but uh, I'm telling you because you could run out of time looking what is happening. So you need the frame name here, not only here, but just a reference name. You have, well, put both here. It helps you. Um, Here are the materials that we're using in Gazebo. So everything that I made on Arvis, I try to make it in the same way and the same color using Gazebo. So we're using transparent blue, white, black, uh, gray, and all are referred to the links. So this is a basic file for Gazebo. This one is for the transmission. When you are working with ROS controls, you want to interface with Gazebo. You need two things. You need to publish the joint states, and also you need the transmission because you have a joint. You have to publish the joint, and you have to tell which joint will have control. So this will help us to do control over the joint that has the motors. This is only for RV's visualization, the materials, the colors that we're using to display black, white, gray, soft blue, green, so on and so on. So here is the long part that you will spend making. So here are parameters that we're using, fixed parameters for the macro. Here I include the inertia macro because I told you that we're trying to do control in Gazebo. Because Gazebo is a physics simulator, we need to calculate the inertias. An interesting thing to know is that if you don't calculate well the inertias or the motor is not well balanced, it will do some odd movements because you have to, in example, cannot calculate the inertia. You can calculate the inertia, but when you assign the inertia to your model, probably it's not well balanced and your robot will deviate to the right or to the left. So try to calculate well the inertias. Here I'm including the inertias because in the macro here I will use it. So we got the visuals in the link. We can do several things. We can do visuals as this is visuals. We also need a collision frame, a collision in the link. On we need to specify which joint is connected with which joint. Also, here I am specifying the inertias. As I told you, we need the inertia for the simulation. Here are the inertia. That's why I'm including the inertias file. So we're trying to do the things like when we are programming in C, C++, Python, any language. So while trying to make it very well documented code of the Sacro file. The same thing for the cylinders or the caster wheels. So you see, everything is pretty neat and simple with Sacro. It's quite complicated at the beginning, but you will get at your own pace understanding Sacro. Here are then the wheels, the same thing. I have included the inertias here, the variables above, and make the wheels macro. Next, the antennas macro, the same thing for the board, The same thing for the camera. This is a little bit long, but you're seeing if you're in a big project, you only seek for the things that you care about. So I will try to deviate this a little thing. You have to just only open one file and not go up and down and see in which part of your XML of your big URDF you are in. So you only open the thing that you're worried about because you segmentate your code pretty well. This is the chassis Sacro. So you see some ones are macros like functions, and other ones are only all the hard-coded file. For example, the camera. I told you that there's no interest to do a Sacro file, a Sacro macro for the camera because we only have one. If we have, if this robot in the future will have 4 cameras, one here, and one here, of course, is valid to do a Sacro macro for use on the Jetbot. But right now, because it's one, just it's not necessary. Here, okay, as you see, it's pretty well documented. I then build the Sacro file using simple macros and includes. I load the ROS controls using Gazebo, and what we can view now is how we interface with Gazebo. Well, with Gazebo, we have to, if you are using the diff right control package, you have to specify some values. For example, the publish rate, which is your left wheel, which is your right wheel. You have to review the ROS controls, differential drag controller. I mean, the differential drag controller package for see why we are putting these things. Basically, these things are needed. Also, there are a lot more parameters that you can put, but those are the basic ones to make the things work. So we have the wheels, this separation of the wheels between wheel and wheel. There are 12 centimeters. Pulse and twist covariance for making a simple odometry. For in the future, if you have an IMU or wheel encoder, this will help. You have to specify the base length, also the linear and angular minimal and maximal velocities, accelerations. So, of course, I told you that we are using or publishing the joints. We need the joint state controller. On this one, I make at the beginning I make the caster wheels movable, continuous. But the only thing that you must know is that we only need the left and right wheels. We can put the caster wheels as fixed, and this will work pretty well. So that's why I have these comments here. So the launch file, okay, this is RB's visualization. When you load all the application, this file is called. So it's only the configuration of RBs to view the robot. This is the world of the Jackson. It's only the ground plane and a Coke just to test the visualization. And finally, we will see the launch files. Let's see which one. Let's see one. Okay, let's see this one. Here we have an argument. We need the robot description as an argument for RBs. We also need guy. This is the RBs configuration. As I told you, we are loading default configuration named jetbot.rbs. Here, then we pass the model to the robot description that will need RBs to start here, then we'll load the joint step publisher guy and uh, launch the nodes for the robot state publisher and also RBs. So this would only load RBs and publish the joint states in the RBs interface. So that's basic, the basic thing using RBs, but we're launching Gazebo. So for Gazebo, it's a little bit more complex, but it's pretty simple also. It's the same here. We're loading the model as an argument, also the RBs configuration. We load the values of the joints, joint state controller, and the differential drive controller package here. Also, we are loading the PID default values. You can tune with dynamic reconfigure, but at the beginning I'm loading it here. When I tune the values, I will put the last ones here. But basically, I'm just loading the dynamic configure. The PID controller here with these values for the left and for the right width. Next, we will include the launch file for launching Gazebo. So we will launch Gazebo here. We'll also launch RBs. Also, we'll spawn all the joints, state controller, and the differential drive. That's why we need this YAML files. And also, we are launching the, you remember the RQT robot steering UI to control the robot to go back, forward, left, right. Well, the manual control of the robot is done here. Next, the most complicated launch file here included is the one with Gazebo, because it's not complicated. It's that it has a lot of arguments. Here we first use the robot description. We launched a word, an empty word at the beginning, but if there's a word named jetbot.word, I will launch a word. Next, we will use a parameter, the robot description, and finally we will spawn our robot in your URDF using this node, and also we will publish the joints and all the information of the robot needed here. So that's all what the application does. Quick things that I learned when you start using URDF, when you want to work with URDF, the first thing that you have to do is to play with visuals. For example, don't try to because how to explain it? With visuals, you have two things to do. You have an orange here, and an origin here. You can also rotate here and rotate here. So which one is the the correct way to do? If you want to move the axis, let's do with an example. Okay, this is the x-axis, the red. The y-axis is green, and the blue is the z-axis. For example, okay, imagine that you want to move the axis. So you create a box. Originally it's at 0, 0 here, not displace it here, and you at the end you want to displace the axis from the middle to this one. You do it here on the visuals because you are moving the object. But when you are trying to put the rotation axis, you put it here on the joint. So let's see where is axis here. Here you put the rotation onto the joint here because it's a wheel. In this case, we will rotate on the y-axis. I'll always try to put R your x-axis in that way, even if your visual is rotated, try to put it on that way. So that's why my wheel is rotating. So since I learned you have to move first the object, do what you want to do here, put an example the rotation properly, because when you load a cylinder is plain like this way, not this way. Try to rotate, then fix everything, and in the end you put the axis of rotation and the orange on the joint. Another thing that I did not do incorrectly, but I recommend you to do is first do a quick URDF and then pass to Sacro, because it's better to do the URDF first. You will get confident and you will get all the knowledge that you want to see what you're expecting about your robot. Next thing that I learned, well, here I did not include the PIDs, but I include with YMLS files. You can do it. I will. I like that way more than including on the URDF, because on the URDF you have to repeat on this joint. On every joint here you just only specify which joint, and that's all. Everything is fine. The other thing that I learned is that ROS controls are useful, and also you have to they are useful, but they are very tricky. As I told you, you need just a polisher, and then you need the transmission. For each motor, you need joint, say polisher. Obviously, all the joints are polished, but you need the joint state polisher and the transmission polish and the transmission control here. Let's see, transmission. You need the actuator, you need the joint inside the transmission. I made it a macro file, a macro sacro. So hope you like the mini project here. I will try to implement some navigation capabilities of the model and try to implement some opacity functions in the future. So the GitHub repository is below in the description. If you want, you have comments or have problems, you just let me know. And the README will be the information to contact me and try to write me an email. I always am seeing the email more than other social networks. So that's all. Thanks.